Disk drive speed front is RPM. This is mph of the disk drive world. Whereas mph miles per hour, RPM stands for revolutions per minute. It's essentially how many times the drive platters spin in a minute. There are 4 popular RPMs that we've listed on the slide. These are 5,400 RPM, 7,200 RPM, 10,000 RPM and 15,000 RPM. Now quite often we shorthand these to 5.4K, 7.2K, 10K and 15K, and we've listed the way we map that on the slide. Now while we're talking about RPM, we mentioned a little bit earlier that drive platters are rigid, and this is really important because if you get to much more than 15,000 RPM, the edges of the drive can start to wobble, and considering how close the heads hover above the platter surface, as we mentioned earlier, any kind of wobble on the edges can cause a head crash, data loss and a broken drive. Another interesting fact on the topic of RPM is that a 15k RPM drive that has a 3.5 inch platter, the outside edges of that drive are moving at over 155 miles an hour. Now then, the RPM of a drive has a direct impact on 3 things. First up, it has an impact on the performance of the drive. More revolutions per minute or more RPM equals more speed. More RPM usually results in less capacity on the drive as well. Slower drives have more capacity, faster drives have less capacity. The third point, faster drives, those with more RPM, also tend to be more expensive. And as for these 3 points we've mentioned, the converse is also true. So less RPM in a drive gives you less speed, less RPM gives you a higher capacity, and less RPM gives you a lower cost per gigabyte. And because we can buy drives ranging from 5,400 RPM to 15,000 RPM, there's a lot of scope for choice there, and trade-offs do have to be made. You may have some applications that require ultra-low response times. They would want the faster drives, let's say 15,000 RPM, whereas other systems that don't quite require the same performance might be happy sitting on 5,400 or 7,200 RPM drives. Something else that significantly affects the performance of the disk drive is seek time. Seek time is how long it takes for the actuator to position the read-write heads over the correct area of the disk. Again, faster is better, but like with most things in life, faster also costs more money. We measure seek time in milliseconds. And while a millisecond to you and me might be an extremely short period of time, in the silicon-dominated world of the computer, a millisecond is actually a very long time indeed. Many computing-related operations are measured in microseconds or nanoseconds rather than milliseconds. As we can see on the slide, a millisecond is 1,000th of a second, a microsecond is 1/1,000,000th of a second, and a nanosecond is 1/1000,000th of a second. So some computing operations are measured in billionths of a second, some in millionths of a second, and when the disk drive is involved, sadly, some are measured in thousandths of a second. So remember when we mentioned earlier on that the disk drive was by far and away the slowest component in most computer systems. I guess we can see why people often refer to them using terms such as spinning rust, rotating rust, and the 3-legged dog of the computer. The impact of a slow seek time on a disk drive is most noticeable when a drive is servicing random read workloads. These kind of workloads are where the disk drive is being asked to retrieve data from locations all over the surface of the drive platters, requiring the read-write heads to be constantly moving to different locations. Transactional database workloads are a common example of a random workload generator. And in extreme examples, it's not uncommon for a disk drive to spend over 90% of its time seeking. So if you have a disk drive that's got a slow seek time, it's really going to impact your performance. Next up on the performance front is yet another mechanical related issue, rotational latency. Sometimes we refer to rotational latency as simply latency. Effectively, it's how long it takes the platter to spin into the correct position. Let's have a look at a quick example to explain this. On the slide we've put a picture of a simplified disk drive platter divided into tracks and sectors. We've highlighted one track in white, and we can see that this track is divided into 16 sectors, numbered 0 through 15. But just for the record, disk drives have loads more than 16 sectors per track, but this is just a simplified example for the slide. Now then, Let's imagine the disk drive receives a read request and has to move the read-write heads to be positioned over the correct track of the disk. The time that it takes for this operation to occur is referred to as seek time, which we just discussed on the previous slide. In our diagram, we've positioned the heads over the track highlighted in white. However, once the read-write heads arrive at the correct track on disk, they'll usually have to wait for the correct sectors to arrive beneath them. Again, in our example, the heads are positioned above sector 4. That's great, but it's no good if we want to read sector 12. In order to read sector 12, we'd have to wait for the drive to perform a full half rotation so that sector 12 arrives beneath the read-write head. Now then, because a drive that operates at 15,000 RPM spins pretty much twice as fast as a drive that operates at 7,200 RPM, the 15,000 RPM drive will be able to position sector 12 beneath the read-write head in only half the time that the 7,200 RPM drive would. That's because one drive spins twice as fast as the other. And of course it's important to remember that none of this mechanical related delay occurs when we're talking about CPU or RAM operations, where everything is silicon and semiconductor based. Now then, while seek time only becomes significant in random workloads, rotational latency is important in random and sequential workloads. Let's take another look at our example disk drive that we've got on the slide. A sequential workload might require the disk drive to read sectors 0 through 15 on our highlighted track. And because it's a sequential workload, the drive will be reading the sectors back in order. So sector 0, then sector 1, then sector 2, all the way through to sector 15. Because this will require a single full rotation of the platter, the faster the RPM of the drive, the faster that the data will be read back. So to recap on this, rotational latency is how long it takes for the platter to spin and get the correct sectors underneath the read-write heads. RPM, or rotations per minute or revolutions per minute, is directly linked to rotational latency. The faster the drive spins, the lower the latencies. And finally, RPM and rotational latency have a direct impact on both random and sequential workloads. The net result being, if you can afford to, buy the fastest drives that you can. Now is a good time to talk about how a platter surface is divided into tracks and sectors.